So next speaker is Fredrik Ekre, who was associated with TU Braunschweig, but now is at Julia Hub. And he's talking about 1 year Ferrite.jl development. So we have a big release coming up, and I guess some of the changes will be introduced now to you, such that you can update your code base if you want to adapt to the new release.
Yeah. Okay, thank you. So my name is Fredrik, and up until the last Monday, I was at postdoc at TU Braunschweig, but now since Monday, I'm working at Julia Hub as a software engineer. Today, I wanted to present a little bit on what has happened since last year's meeting, when we were having the first edition of this conference at TU Braunschweig. So that's the goal of this presentation. So for my agenda here, first I want to just look at some of the repository statistics, what's happened since last year. I also want to discuss some of the changes to the documentation, because we have reorganized it quite a bit, and I'm curious, or I wanted to present this here, and curious about some feedback on this later on. And the main part would be to discuss the features and the ongoing development since last year. And then, as Maxim mentioned, we are working towards the next release. And then finally, I just want to mention a little bit on how you can contribute to the project. So now it's maybe a little bit difficult to see here, but these are the statistics since last year. So here we met 1 year ago, and you can see that in this year, it's been quite a lot of development compared to the previous 7 years when Christopher originally started it back in 2015. So this is what me and Christopher did during our PhD, and then a little bit more happened when more people got involved. But we've had 7 releases in 1 year now, 218 commits and 715 total. So during this year, there have been 20 people contributing to the project, and in particular, I think it's nice that there are 11 new contributors. So in total, there are now 30. So it's nice to see that the project is growing and more people get involved. So for the documentation, I will upload the slides later on, but we have made some changes. So there's a completely new structure. Actually, maybe we can have a look here. You can still see it here. So it's now only available in the development version. But we are now following a different kind of framework, which is called, I lost my, this one, so it's called diataxis, which is some documentation framework for how to structure your, now I completely lost my way here. Here we are. Okay, so now the documentation is structured a little bit differently. So there are 4 main sections, which are tutorials, which are meant to teach a bit and introduce the concepts. We have now topic guides, which are more in-depth explanations. There's a reference sections with more technical API documentation, and then some how-to guides for more specific topics. And now there's also what we call a code gallery, which is more, maybe not so much for teaching Ferrite, but to show off what you can do. So if you do something with Ferrite, please contribute here and share it with the rest of the community. Yep. Oops. Okay, so that's I think this is pretty nice split between these different sections. And if you haven't looked at it, please do, and share your thoughts on this. So I mentioned the code gallery, so please contribute. And finally, we have now also started documenting the internals of Ferrite a little bit. So hopefully that will also make it easier for others to contribute. All right, so let's move on to the features, which are, I guess, the fun part. So first, I will talk about features I will not talk about, because others will during this day. I just want to mention it because that's kind of the major things that has happened since last year. And then I will cover some more specific things that has also happened. So we had a summer project sponsored by Google this year, which was executed by Abdul Aziz on discontinuous Galerkin methods. So there's been going quite a lot of features related to this, and I will not say anything more because there will be a presentation in this afternoon about this. We have worked quite a bit on the degree of freedom handler or DOF handler, and there's now includes a lot of more features for this, and there will be a talk by Kim. There are ongoing work on mesh refinement, which Maximilian will present today as well. And the final thing I want to mention that is the distributed computing, which is Dennis' parts, and he will share some progress updates on this also this afternoon. So these are all pretty say major things that's been going on since last year. And then let's look at some, let's say, smaller things. So the features that I will talk about because no one other seems to care, perhaps. Okay, so the first one, which I think is pretty neat, is what I call local application of boundary conditions. So what does this mean? Well, to the left here, you see kind of the pseudocode for how you assemble and solve a finite element problem. So you have some for loop, you loop over all of the elements. For each element, you compute the local matrix. And when you have this matrix, you assemble it into the global sparse matrix. So we do this. And when we're done, we need to think about the boundary conditions. So I'll show later on how we do this, but basically we need to zero out some rows and columns which correspond to the degrees of freedom which are prescribed. So after we do that, we can solve the linear system. So in this case, it's what I call global application because we apply boundary conditions on the global matrix after the assembly. So this is, let's say, the standard way, and it's pretty easy because you do exactly the same thing, of course, for every element. You don't care about the boundary conditions until you're finished. But now in Ferrite, you can also do what I call local application. So if you look to the right here, it's more or less the same, but we have now moved up this third step for applying boundary conditions into the loop. And particularly, we do it before we do assembly. So we still have a loop over all of the elements, of course. We compute the local matrix, and then we apply boundary conditions on the local matrix instead. So we zero out any prescribed rows or columns. And then we have a local matrix which respects the boundary conditions, and then we assemble this one into the global matrix as the third step. And then when this assembly loop is finished, then the global matrix already respects the boundary conditions, and then we just need to solve at the very end. So I try to make some visualization of this procedure. So step one, compute the local matrices. So these are the dense white blocks here to the left. And then we have our global sparse matrix on the right-hand side. And of course, we take our local matrices and we insert them into the correct spot in the global matrix like this. So if we do global application, then basically when this global matrix is complete, then we identify the degrees of freedom which are prescribed. We zero out the corresponding rows and columns. And then we have a linear system that we can solve. So, but if you look at this picture here, you can kind of see that it's possible to switch step 2 and 3 here. Because if we look at this blue or teal box here, this red line, which is the zeroing out of this column, which let's say corresponds to degree of freedom 100, it looks like we can do this on this dense block right here. We can do this on the local matrix instead. So if we flip it around, that would correspond to something like this, right? So maybe if we take one step back. So in this case, there is just, let's say, 2 degrees of freedom which are prescribed. So one is somehow related to the first element in this picture, and one is related to the third one here. So there's nothing going on, or no zeroing out in the middle element here, and that would correspond to something like this. So for the first element, we need to zero out some rows and columns, and for the last one, but not for the middle element. So why would you do this? So you can, of course, argue which one would be most suitable. So in both have, I guess, advantages and disadvantages. So in the global case, you have to work with the sparse matrix structure, which isn't always trivial. If you do like a serial computation, it's pretty easy, but you still have to, since all of these non-zeros are not stored, you still have to identify which entries in the matrix needs to be zeroed out. But at least you only do it, let's say, once, because in general, there will be elements overlapping. So if you do it locally, then you, let's say, zero out the same row multiple times. But the advantage of doing it locally is that then you just have the standard matrix that you're working with. So the local matrix is just the standard dense matrix. So it's very fast to zero out the row and column in this one. And the other advantage is that now when we build the global matrix, it's correct from the start. So you don't need to modify the sparse structure after. And this is in many cases, or for some sparse matrix structures, for example, when doing distributed computing, then it's not possible to go in and modify this one after the fact. So then you have to do something like this locally so that the matrix that you build is the correct one. So as I mentioned, you can do this in Ferrite now. Here are the pseudocode. So to the left, we have the standard setting where you compute called KE, so the stiffness matrix for one element. And then you assemble this one, and then we apply after the loop. Or what you can do now is that you can, there's a new function now called apply local, which zeroes out the rows and columns in the local matrix, and then you assemble, and then after the loop, you just, then you can solve it directly. Okay, so that's one new feature, which I think is pretty cool. The other thing, which has existed for quite some time, but not with nice interfaces, let's say, is to renumber the degrees of freedom. So by default, Ferrite numbers, we loop over all of the elements, and then if you have multiple fields, then we go field by field. So the ordering of the degrees of freedom will basically be element by element. So in some sense, this is a random order because the elements might be in random order if they come from some mesh library. And of course, this is not always optimal. So there are now functionality to renumber based on, for example, your fields or your components. So this means that you will get a global blocked matrix. And I will show an example of this one later on. So let's say you have a problem with displacement and pressure. Then you can collect all of the displacement degrees of freedom in the first block and all of the pressure degrees of freedom in the second one. And then you get a global block matrix. There's also now support for doing renumbering based on Metis, which is the library for doing several things. But it can one thing it does is to compute the permutation to reduce the fill-in of the matrix. So I have an example of these ones here. So this is taken from the documentation. So this is the weak form for Stokes flow. So we have two equations. We have two unknowns, displacement and pressure, like this. And if we look at the corresponding sparse matrix, so to the left is the default, let's say, random order. To the right is now renumbered so that all of the displacement degrees of freedom are located first, and then all of the pressure. But it's pretty difficult to see in this image, and it actually looks like the right one is more dense, but this is just an artifact of this sparsity pattern plotting. So I made another attempt at visualizing this. So now to the left, we have, let's say, the default order, which is element by element, right? So we have displacement, pressure, displacement, pressure in both rows and columns. So then you get this kind of pattern where the green blocks are couplings with the test function for displacement and displacement itself, and so on. But if you reorder it based on the fields, then everything related to U becomes, is moved to the first block, and then you get this global block matrix. So this is a pretty nice feature if you have some specific solver that wants to work with the individual blocks. Of course, if you're just going to use an LU factorization, I don't think it shouldn't matter. But if you have some algorithm that wants the access to the blocks, then this is pretty nice. And then also the renumbering with Metis. So Metis tries to reduce the fill-in, as I mentioned. So to the left is again the standard order for some small finite element problem, and to the right is the sparsity pattern, which is reordered. And of course, it has the same number of values; they are just permuted. But you can see that you get, like, let's say, some structure that is at least quite different from the original one. So this in itself doesn't really gain you anything. But if you look at the sparsity pattern of the Cholesky factor, for example, so to the left is with the default numbering, and then you can see that you get approximately 16% stored values going, and originally it was 5. So this one is quite a lot denser. And to the right is the same factor for computed on the reordered one. And then you can see that this is much more sparse. So this is just 6%. So I think the solvers that Euler uses does this on its own. But if you the Cholesky solver, but of course this can also be useful if you do some incomplete LU or Cholesky factorization, then you get a smaller memory footprint in this case. So there is also now some functionality to reduce the original sparsity pattern. So there are basically 2 things which you can do. And the first thing which I mentioned here is to specify the field coupling. So again, looking at this same weak form, Stokes flow. So if we go back to this one here, we can see that in the first equation, there is coupling between delta U and U, between delta U and P. And in the second equation, there's coupling between U and delta P, but there is no connection with delta P and P. So basically, if we maybe if you look at this image again, this pink block here on the lower right, well, there will be no entries there. So it's unnecessary to allocate this memory. And you can do that now, or you can ignore those now. So it's possible now to specify the coupling between the fields. And in this case, to the right here, I have said that there's no coupling between p-DOFs and delta p-DOFs and p-DOFs. So this lower right block here is 0, except that we still keep the diagonal around because it's beneficial for the solver routines. So this reduces the memory footprint a bit as well. And then there is one minor thing, is that you can eliminate the constrained degrees of freedom, because as I mentioned before, these are things that we will zero out anyway. So they don't really need to be in the matrix to begin with. And typically the number of prescribed degrees of freedom are not so many compared to the total ones. So, but in this case, you have started with 18,000 non-zeros, and if you remove all of the prescribed ones, you get down to 15,000. So at least it's something. This will be more pronounced if you have, let's say, some very refined mesh at some boundary where you have a lot of prescribed degrees of freedom and so on. But in this image, it's pretty difficult to see the difference. Okay, so then I also want to mention some smaller niceties. So the constraint handler and Dirichlet boundary condition types have gotten some changes. So in particular, now all of the components of a specified field is prescribed. So previously we assumed only the first one, which was pretty strange if you had a vector valued problem. You can now prescribe values as a function of just x. So previously you had to do f of x and t, so coordinate and time. But in many cases you don't have a time dependent problem, so now you can ignore this completely. And the third point here is also related to that, is that after you define all of the constraints, you had to call update previously to recompute all of the values, but now this is happening automatically. So if you don't have a time-dependent problem, it simplifies things quite a bit. You can also now do periodic constraints with rotations. So that this is the Stokes example again. So now we have periodicity in the velocity. So the y velocity at this edge is periodic with the x velocity or the minus x velocity on this outlet or inlet. And okay, I'm running out of time, so I just want to briefly mention that boundary integration has been made a little bit easier thanks to some changes with Knut. We have made some changes which hasn't been released yet, but we have. So previously we had this reference shape, which is basically the element shape, and previously we did parameterization with the dimension, starting with 3D. So a cube in 3D, or it's a hexahedron, and then a cube in 2D is what we used to call a quadrilateral, for example. But now these have explicit types, which simplifies things a bit. So yeah, the green is what you can do now, and the red is what you did before. So for example, when you define the interpolations, so previously if you had a Lagrange interpolation in 1D, you had to write dimension 1 cube, but now you can actually say that you have a line element, first order, and so on. And in particular, this also enabled, now we have a specific phase quadrature rule instead of just a quadrature rule. So to the right here on the two bottom ones here, you can actually not see a difference whether this is a quadrature rule for an element, 2D element, or if it was a quadrature rule for the phase of a 3D element. But now we actually make a difference. So you can ask for the quadrature rule of a quadrilateral or a phase quadrature rule for the hexahedron elements. I think this is the last content slide, so I will just do this quickly. So the interpolations has also changed a bit. So now we divide them into scalar or vector interpolations. And all of the existing interpolations are scalar. Now you have to explicitly say that you want it to be vectorized. So if you have the scalar interpolation, let's say we have 3 degree shape functions, now you need to explicitly vectorize it and get these vector shape functions like this. This allowed us to merge these object cell scalar values and cell vector values. So now this is just cell values, and then you let the interpolation determine the vectorization. And yeah, okay, this was the final thing. So this also enabled embedding. So we now make a more clear separation of the different dimensions. So we have a reference dimension, which is, let's say, the element shape, the spatial dimension, which is the spatial domain where this is embedded in, and then also the vector dimension if you have a vector value problem. So this is an example where we have 2D elements embedded in 3D space as a sphere. Okay, and then look at the, wait, okay, this one is stuck. That's strange. The GIF, okay, I switched to the next slide, but maybe I do this.
Reshare?
Yeah, I thought I did.
I guess it's internet connection.
Okay, yeah, I lost the connection apparently. Okay, but the change log at the repository has a lot more changes. So please have a look. And let's see if I can connect to the meeting. Otherwise, I'll just finish without the last slide. So there's also, we have written like a contributing guide. So we can also find this on the repository, which has some documentation on how you can contribute. So please do. Okay, that was my presentation. Thank you.
Okay, any quick question for Fredrik? Yeah.
When it came to the structure of the global matrix and using it as kind of software, I think typically you need each block to be like an individual.
Yeah.
If there's like a plan to have like a box part of the matrix that has like.
Yeah, you can already ask for that actually. So then if you use the block arrays package, then you get individual. I mean, that uses separate blocks, right? So yeah, I mean, otherwise it's not really useful to have this global block structure unless you plan to extract the individual components. Yeah. Yeah.
Another quick question is about for local elimination. How does it play with FE constraints?
Yeah, so that's something I skipped over now, but basically, so what Dennis mentioned, theme constraints is something that couples not only locally, but maybe to, let's say, in the periodic case, it's coupled, you have coupling between degrees of freedom on separate sides of the domain. And in this case, it's not possible to only zero out locally because you need to distribute these contributions to other degrees of freedom. So there is this functionality which you can, in one go, apply locally and assemble, basically. So you can think of it as a lens, perhaps, that you take your local matrix and then push it through this this lens into the global system, and then it will add to the other locations.
Then thank Fredrik once again.